Hi everyone, today we're going to do implicit differentiation. We'll still be using our rules, but just in a different way. We should start by talking about what do we mean by implicit. Easiest way to explain implicit is to talk about explicit. An explicit equation expresses the dependent variable in terms of the independent variable. Basically, this means that the equation is written in the form y equals something or f of x equals something. So we are very used to getting explicit equations. Our independent variable is x, our dependent variable is y. We plug in x, we get out y. Some examples you might be used to look like y equals x squared plus 4 or f of x equals 3x plus 2. But what we're seeing here is we're solved for y or we're solved for f of x. An implicit equation relates the variables involved but is not solved for a particular variable. This means the equation is not solved in terms of y or f of x. Examples could be x squared plus y squared is 9 or 2x minus 4y is 12. These particular equations imply the value of y based on any given value of x. So we could still plug in x and get out y, but we would have to do some work to get our final value. Good news is our notation doesn't really change. We are going to write the derivative of y as y prime no matter where the y is in the equation. So if it's at the beginning or kind of mixed up in the middle, we're still going to write y prime every time we take the derivative of y. So we're going to do some examples where we'll do the derivative two ways. We're going to find y prime given 3x plus y equals 6. The first time we'll find the derivative by solving for y first. So from 3x plus y equals 6, we can make a quick change to y equals negative 3x plus 6. Now when I take the derivative, y prime equals negative 3. We're going to do that again, but now implicitly, which means don't change anything around. Our 3x plus y equals 6. Derivative of 3x is 3. Derivative of y is y prime. Derivative of 6 is 0. I can still get y prime by itself by moving the 3 to the other side. We can go back and compare. We got negative 3 with an explicit equation. We got negative 3 with an implicit equation. So things aren't really changing. It's just how we go about it and our starting point. Example 2. Find y prime both explicitly, solving for y first, and then implicitly. So we're starting with 4x squared plus 2y equals 12x minus 80. I'm going to solve for y. So I have 2y is negative 4x squared plus 12x minus 80. Let's divide by 2. I get negative 2x squared plus 6x minus 40. Now I can find y prime by taking the derivative. Negative 2x squared becomes negative 4x, 6x becomes 6, and the 40 is gone. Let's try that again. This time we're going to leave the function alone, and we're just going to go through and take the derivative. 4x squared becomes 8x. The derivative of 2y is 2y prime. Now that might take you a while to get used to. You're going to do derivatives like before you're doing the power rule. But even though we took the derivative of 2y, we want to hold on to the fact that the 2y was a y, it wasn't an x. So when we're taking these derivatives, we're taking the derivative with respect to x. So y has to get a prime every time it appears. 12x, the derivative is 12, and the 80 is 0. It goes away. I want to again solve for y prime, so I'm going to leave the 2y prime on the left. I'm going to move the 8 over. Now I have negative 8x plus 12. Dividing by 2, y prime is negative 4x plus 6. We'll take a really quick look back and see we also had negative 4x plus 6. So your big trick, your big thing you want to think about is every time you take the derivative of y, you put a y prime next to it. All right, here's one where we can't separate it. So this doesn't look like the functions we've had before. This is just an equation. I have y squared equals 2x cubed. When I take the derivative, y squared becomes 2y, so that was my power rule. But I took the derivative of y. It needs a y prime. 2x cubed is 6x squared. I want to solve for y prime. I'm going to move the 2y over. So y prime is 6x squared over 2y. This part should look new too. Before, we never had y's in our solution. We would always have just x's. So as you're going through and solving, just keep in mind what you're trying to do. You're trying to get y prime by itself. If the answer has a y, that's perfectly okay. Now that we have our derivative, we're going to find the value of y prime at the point 2, 4. So y prime equals, I have 6 times 2 squared over 2 times 4. 2 squared is 4, 4 times 6 is 24. 2 times 4 is 8. So I have 24 over 8 is 3. This still has that same idea of what's happening here. So when x changes from 2 to 3, we expect y to go up by 3. If you wanted to really see what that looked like, let's put y squared equals, and I'm going to do 2 times 3 cubed. So what was my idea? I'm going to increase 2 from 2 to 3, and let's see what's going to happen to y. So y squared is going to be equal to 3 cubed is 27, 27 times 2 is 54, and then I'm going to take the square root. So the square root of 54 is 7.34. It follows what we said would happen. Our value had been 4, it's going to go up by about 3, 4 plus 3 is 7, and we got 7.34. The next one says 4y squared plus 6y equals x cubed plus 9x. Stop a minute to notice y is in this equation twice. I have a 4y squared and I have a 6y. My warning is wherever you have a y, you put a y prime. Maybe it's not a warning, maybe it's just that that's our rule. So I have 2 y's, it means I'm going to have 2 y primes. Super important that you see that. 4y squared becomes 8y times y prime. 6y is 6y prime, and that's equal to 3x squared plus 9. Now that I have 2 y primes, the goal is to only have 1. So the way we're going to accomplish that is to factor out the y prime. So I'm going to take it out. I have 8y plus 6. I know that 8 and 6 have 2 in common, but I'm not going to take it out. My goal is to get y prime alone. I don't care about any other factors. On the right side, I have 3x squared plus 9. To get y prime by itself, I'm going to divide by 8y plus 6. I have y prime equals 3x squared plus 9 over 8y plus 6. Let's again find a value. We're going to put in the 0.33. I have y prime equals 3 times 3 squared plus 9 over 8 times 3 plus 6. You can put that in your calculator, you get 36 over 30, then you could reduce that down to 6 over 5. This says when the value of x goes up from 3 to 4, we expect the value of y to go up by 6 over 5. Let's try it again, throw in an e. Here I have e to the y plus 5 equals 2x plus 8. I only have one y, so I'm only going to have one y prime. It's going to come from the e to the y. So e to the y times y prime. Feels like the chain rule there. 5 goes away. 2x plus 8 becomes 2. My y prime is 2 over e to the y. One more time, we have a value. We want to know what's the value of y prime if I put in -1, 0. And you may think, well, what am I going to do? How am I going to put in -1, 0 when I don't have an x? And it's really not a problem. I say y prime is equal to 2 over e to the 0. 0 is the value for y, so I put it into the exponent for e. E to the 0 is 1. I get the value of 2. The next one says y prime is 4y cubed plus 6y equals 7x squared plus 9x minus 3. Couple things to stop and look at before I start. Number one, I have 2 y's, which says I'm going to have a y prime. I also have a 6xy. The xy's are being multiplied together, so I want to add a little rule here that this is the product rule. So the product rule is occurring because I have the x and y touching. Start with 4y cubed, that becomes 12y squared, and we know we have to attach a y prime. 6xy, product rule. Let's start with 6x, the derivative is 6, keep the y. Change that, go back to 6x, derivative of y is y prime. Equals 7x squared is 14x. 9x just becomes 9, and the 3 derivative is 0. My goal is to get the y primes together. So I have a y prime in the first term, a y prime in the third term. Let's go ahead and write those two together. 12y squared y prime plus 6xy prime. And I'm going to move the 6y to the left. I have 14x minus 6y plus 9, and this order on the right doesn't matter. Let's take the y primes out. Y prime comes out. I have 12y squared plus 6x equals 14x minus 6y plus 9. Y prime is equal to 14x minus 6y plus 9 all over 12y squared plus 6x. Okay, this looks a little complicated. That's perfectly okay. It's calculus. We kind of think things are going to get complicated. But be careful. Go back and check your steps. It's easy to mess things up, and the best way to catch it is just to look it over again. Let's try 2x cubed y to the fourth equals 10x plus 6. Well, good news, we only have one y, but the y and the x are side by side again, so once again, this will be the product rule. Let's start with 2x cubed becomes 6x squared. Keep the y to the fourth, plus, go back to 2x cubed. Y to the fourth is 4y cubed times y prime. Really necessary to have that y prime or we have nothing to solve for. 10x is simply 10. Before I start moving things around, I see this 2 and this 4 can be multiplied together, so I have 6x squared, y to the fourth, plus 2 times 4 is 8x cubed, y cubed, times y prime is 10. I'm going to move the 6x squared y to the fourth first. I have 8x cubed, y cubed, times y prime equals 10 minus 6x squared y to the fourth. Now I'm going to divide by 8x cubed y cubed. I have y prime equals 10 minus 6x squared y to the fourth over 8x squared y cubed. Right, and I'm going to be picky for a minute. I have a 10, I have a 6, I have an 8. Notice 10, 6, and 8 are all divisible by 2, so let's go ahead and simplify that. 10 divided by 2 would be 5. 6 divided by 2 would be 3. I still have x squared and y to the fourth. And then 8 divided by 2 is 4, x squared, y cubed. I don't do this to be mean. I do this because I want you to get the right answer when you're doing the homework and not be confused when all of a sudden a 10, a 6, and an 8 become a 5, a 3, and a 4. Now I have y prime is equal to the natural log of y plus 3x equals 2y minus 8. Hopefully you're starting to see the first thing I should be looking for is the number of y's I have, and I have 2. I start with the natural log of y, which you know the y goes on the bottom, and you're going to put the y prime on top. Every time I have a y, I get a y prime. 3x reduces just to being 3 as a derivative. 2y is 2y prime. 8 goes away. I have these y primes that need to come together. I'm going to keep the y prime over y. I'm going to bring the negative 2y prime over, and I'm going to push the negative 3 to the right. Well, it was 3, but now it's negative 3 on the right. Remember, we want to factor out the y prime, so it's going to come out. I'm going to have 1 over y minus 2. This is negative 3. So y prime comes out, I look at what's left. I have the y on the bottom, it needs to stay a fraction, the 2 stays. I'm going to divide by 1 over y minus 2, 1 over y minus 2. And I know you're probably ready to stop right now and say like, okay, I'm done, I got y prime, but notation-wise, this isn't very pretty. I have a complex fraction. The thing that's really making it a mess is the 1 over y, so I'm just going to multiply the top and the bottom by y. I'm really just multiplying by 1. Y over y is 1. So I haven't changed anything by doing it, but it makes it look better. So 3 times y is 3y. Y times 1 over y is 1 minus 2y. So this is just notationally a better way to write the answer. So that was called implicit differentiation. Next time we're going to do something called related rates, which will just bring in the application. So on purpose I put no application here. I wanted to get into how do we do this, and then I'll add the application in our next video so we can see how we use this in the real world.